Now I will move on to problem number 4. First I will read the problem. The dimensions of a three-stage single-acting reciprocating air compressor are given below. So this is the problem of three-stage single-acting reciprocating air compressor. So is the data is given here. LP cylinder bore is 450 mm. So this is the first cylinder diameter is given 450 mm and the stroke length is given 300 mm and the clearance volume of the first cylinder is given 0.05 of swept volume Vs, and the pressure and temperature of the air entered into the LP cylinder, that is the first cylinder, are given 101 kilopascal and 20 degrees centigrade. The delivery pressure is given. So after the third stage, the air delivered at the pressure of 1.5 megapascal and the index is given 1.3 value. Assume ideal intermediate pressures and perfect intercooling. Determine intermediate pressures, effective volume of the LP cylinder, the condition of air delivered, the work done per kg of air, and R value is given 0.287 kilojoules per kg Kelvin. So here assume ideal intermediate pressures. We have already derived ideal compressor. So pressure ratio in each cylinder it will be same. So this is called the ideal intermediate pressures. And the perfect intercooling means yeah, the air, the temperature of the air leaving the intercooler, it will be reduced to the initial temperature. So first I will explain the PV diagram here. I will explain the PV diagram. So this is the first cylinder. I have already said first cylinder is called the LP cylinder, that is low pressure cylinder whose volume is always more than the other cylinders. For the first cylinder, it is V1 minus V9. V9 is the clearance volume for the first cylinder. So V1 minus V9 is the swept volume. And the effective swept volume is V1 minus V10. This is the effective swept volume. Actual volume of air that should be sucked during the suction stroke in the LP cylinder, it must be equal to Vs. But due to the high pressure of air present in the clearance volume, the actual volume of air entered into the cylinder is the effective swept volume VAS, that is equal to V1 minus V10. So after compression, this volume, it is compressed to the V2 minus V9. So in the first cylinder, the volume of air leaves the first cylinder is V2 minus V9. So this volume, V2 minus V9 volume, it entered into the intercooler. So where its temperature is decreased to the initial temperature. So its volume will be decreased. That is the volume V2 minus V9, it is reduced to the V2 dash minus V9. So from the intercooler, the volume V2 minus V9, this much volume of air entered into the intermediate pressure cylinder, that is second cylinder. So here it is compressed to the V3 minus V7. V7 is the clearance volume for the second cylinder. So after compression, the V2 dash minus V9 volume is compressed to the V3 minus V7. So this V3 minus V7 volume of air entered into the second intercooler where its temperature is decreased to the initial temperature. That is T2 dash. T2 dash is nothing but T1. So when it is decreased, the temperature is decreased in the second intercooler, its volume will be decreased. That is, the volume V3 minus V7 is reduced to the V3 dash minus V7. This volume, it entered into the third cylinder, that is the high pressure cylinder, where it is compressed to the V4 minus V5. So then after that it entered into the next intercooler and so on. So now I will first ask the find out the effective swept volume. He has to find out the effective swept volume. That is V1 minus V10. These values we have to find out first. V1 and the V10. This is effective swept volume. First I will find out the VS swept volume. V4 by sorry, pi by 4 into d square into L. This is the effective, sorry, the swept volume of the first cylinder. D is given, L is given. Substitute the values and I get the 0.048 meter cube. This is the swept volume of the LP cylinder. We know that V9, this is the clearance volume of the first cylinder is Vc. That is V9 is equal to Vc. That is the clearance volume. It is given. That is 0.05 of the swept volume. 0.05 into swept volume we have calculated. It is 0.048. That is equal to 0.0024 meter cube. This is the clearance volume of the first cylinder. Now we can easily calculate the intermediate pressures. That is, in the first cylinder, the pressure ratio is P2 by P1. In the second ratio, it is P3 by P2. In the third ratio, it is P4 by P3. In each cylinder, the pressure ratio will be same. That is ideal pressures. That is equal to Z. So the pressure ratio will be same. That is equal to Z. We know that I have already derived in the derivation. That is Z is equal to Pn plus 1 divided by P1 whole to the power of 1 by X is equal to. That is 150 is the final pressure. It is given and initial pressure is 101 whole to the power of X is number of stages 3. Z pressure ratio is given 2.46. So when it is given, we can easily find out P2 is equal to P1 into 2.46. That is P1 value I substituted is 248.46 kilopascal. So P3 is equal to P2 into 2.46. That is 248 into 4.46 into 2.46. 611.212 kilopascal. In the same manner, P3 into 2.46, it is 1503.6 kilopascal. So I have explained here with the flow diagram. We can find out the V10. So by applying this, P9 V9 whole to the power of n is equal to P10 V10 to the power of n. So in this V10 we can find out. So this is equal to 0.0048 meter cube. So V10 is equal to this much calculated. V1 is equal to, we know that Vs plus Vc. 0.048 Vs and plus 0.0024 is the Vc. That is equal to V1 is equal to 0.0504 meter cube. Ves effective swept volume is equal to V1 minus V10. V1 is 0.0504 minus 0.0048. That is equal to 0.0456. This is swept volume of the first cylinder, effective swept volume. Condition of air delivered. So final condition. So final condition, final temperature is T4. And T4 by T3 is equal to P4 by P3 dash whole to the power of n minus 1 divided by n. We know that this is already, this equation we have already used this relation. So T4 is equal to T3 dash into these values I have substituted. I have got 360.7 Kelvin. We know that PV by temperature, PV by T is equal to constant. For the delivery condition and entrance condition, that is the suction condition and delivery condition, if we apply P is P4, final temperature, delivered temperature, and volume, what volume of air is delivered? It is V4 minus V5. V4 minus V5. This volume will be delivered. And temperature is T4 is equal to. In the first cylinder, the pressure is P1. And what volume it will be entered? It's V1 minus V10. That is the effective swept volume. Temperature is T1. So if you just substitute these values, all these values, we can obtain the V4 minus V5. That is equal to 0.0038 meter cube. So we have obtained the volume condition of the delivered volume. Volume we have calculated and temperature also we have calculated. Next, work done per kg is given. Work done is equal to n divided by n minus 1 mR P1 into P2 by P1 whole to the power of n minus 1 divided by n minus 1. Because he has to find out per kg, m it becomes 1. So it is equal to 3 stages. It is, hence I have given the 3 multiplied by n 1.3 divided by 0.3 into 1 into 0.287 into 293, 2.46 whole to the power of 0.3 divided by 1.3 minus 1. This is equal to work done per kg is through 252.4 kilojoules per kg. So this is the